Now let us discuss another approximate method, and that is actually the Rayleigh's method. And you know, in Rayleigh's method, it is assumed that the dynamically deflected shape, the dynamic deflections actually are proportional to the dynamically deflected shape is proportional to the statically deflected shape. So now suppose there are two discs mounted on this shaft, and the shaft is simply supported, and here this is a static deflection due to the weight of the disc. Here also actually we are measuring this y1 and y2, though we have not shown it here, from the statically deflected shape, and the deformation due to the inertia forces, these are the dynamic deflections due to the inertia forces. Anyway, so here y1 and y2 are the deflection, dynamic deflection from the statically deflected shape. Now you know the kinetic energy is half m1 y1 dot square plus half m2 y2 dot square, and if you write it in matrix notation, this is like this. This is the mass matrix. Now if you consider that this thing is vibrating, the oscillation is harmonic, that means this reaches its maximum, this reaches its maximum, then it becomes zero. When it becomes zero, this also becomes zero, then it goes this way. So this point vibrates like this with a harmonic motion. This point will also vibrate in a harmonic motion, and the maximum in this direction for this and for this occur at the same instant. So this small y1 is this small y2 is this, and this is the maximum kinetic energy. If you put this is the maximum value of y1, and this is the maximum value of small y2. This is the amplitude actually. So if you replace it here, this is like this. Now if you assume that this y1 and y2 is proportional to the static deflection, so and if you put it here, then maximum kinetic energy is this. Now what is the maximum potential energy? The maximum potential energy, that means the when you take the maximum deflection, that maximum deflection multiplied by the forces which are causing this maximum deflection. Which one are causing capital Y1 and capital Y2? Because we know that capital Y1 and capital Y2 being amplitudes, they are the maximum deflection. Now what forces can cause capital Y1 and capital Y2? So if you think of your flexibility matrix or the influence coefficients, then F1 max and F2 max are creating capital Y1 and capital 2. Then this is the relation between capital Y1, capital Y2 and F1 max and F2 max. That means the maximum potential energy is, you replace this by A1, A12, A21, A22 inverse, Y1, Y2. So, and again now you know these are proportional to the dynamic shape is proportional to the static shape. So this is k into this, and this is again k into this, and this is this. So this is k square y1 static y2 static transpose. Here I have missed the transpose. So transpose y, and what is this? This is a1 a12 a21 a22 inverse y1 static y2 static. So this is nothing but the static weights. And what are the static weights? The w of this, weight of this, and the w of this. So this is one important thing which you should remember, that this is nothing but w1 w2, because w1 and w2 are actually causing this static displacements. So in place of this we are putting W1, W2. Now if you equate maximum kinetic energy to maximum potential energy, which we do in Rayleigh's method, then this k square get cancelled from both sides and this is what you get. So this is this. So omega square is this, W1 is G into M1 and W2 is G into M2 is this. And if there are n DOFs or n disks are there, so this is this. Sometimes we omit this static symbol, static suffix, and we write it like this. So this is a problem where on a shaft two discs are mounted. One, this is 225 kg and this is 135 kg, and these are the gaps. Obviously the gaps are not in the drawing, they are not proportional to the drawing is not proportional to whatever is shown here, dimensions. So omega square is this. Now what is y1 and y2? y1 is deflection here and y2 is deflection here, and y1 is actually the deflection here due to this and the deflection here due to this. If you sum them up, then you get y1, and this y2 is the deflection at this due to the weight, this weight, and due to the weight of this. Now the formula we'll be using is this. So if you give a force W here, so this is W. If you give a force W here, if you give a force W here, then the deflection at any x, y axis W bx. What is b? B is the right hand side of W, the length of the right hand side of the W. W bx by 6il L square minus x square minus b square. But this x has to be less than L minus b. That means x has to be left to the point of application of W. So now if you put a weight here, so y1, the deflection here is y11 plus y12. So this is deflection at 1 due to force at 1 and deflection at 1 due to force at 2. So now if for this, okay, for this one, so if you apply a force here and if you want to calculate the deflection here, then this formula is valid because x is equal to L minus b. If you apply a force here and you want to find out a deflection here, so this is b and this is L minus b, so x is equal to L minus b. So in this case b is actually 3. For y11 b is actually 3 and x is 2.5, and then L square minus x square minus b square is 6eil. So this is y11, and y12 means the load is here and you are finding out the deflection here. So x is this much, so x is obviously less than L minus b. L minus b is this much. So there is 135 g into b is, the load is here, so b is 1.5 and x is again 2.5, and here 5.5 square minus 2.5 square minus 1.5 square is this. So if you sum these two up, then you get y1, and for y21 will always be equal to y12, but still if you want to find out y21, that means deflection at this point due to this. Now see, you cannot use the formula like you cannot take x from the left hand side because x is here, so you cannot find out the deflection here. Yeah, so you have to find out y21, so deflection at 2, so x is now greater than L minus b is this, the left of the load, L minus b is this, but x is this, so x is not less than L minus b, so you cannot take x from this side. So what we do is we take x from the right side and take b here. So now x is less than L minus B, because this hole now has become L minus B. So here 225 G, so B is now this much, so this is 2.5, and x is now this much is 1.5, so 5.5 square minus 1.5 square minus 2.5 square by this you can check, this is equal to this, and this has to be like this, y12 equal to y21 according to Maxwell-Bettys reciprocity theorem, and y22 is force at this and deflection at this. Here you can take x from here or x from here, whichever you like, and this is 5.5 square, x is 1.5 and b is 4. So using this you can get this as your y, y2, y1 and y2, and once you get your y1 and y2, so you can use this formula and you can get your omega. So this is actually the value of omega, and again you can do it by Dunkerley's method. So 1 by omega 1 square, that is the first natural frequency square, is approximately equal to A11 M1 plus A22 M2. A11 means due to unit load, that means here you put 1 here actually. So unit load, that means if W1 is 1, if W1 is 1, then what is the deflection, that is A11, and A22 is, if W2 is 1, then what is the deflection at this point. So this gives you, this without this weight gives you A11, and this without this force gives you A11. So A11 M1 and A1 A22, this gives you A22, sorry, this without the force gives you A22. So A11 M1 plus A22 M2 is the 1 by omega 1 square, that gives you this as your omega 1. So always remember that the Rayleigh's method gives the upper limit and the Dunkerley's method gives the lower limit. So both are approximate methods, and one gives the upper limit and other gives the lower limit. So now a given beam was vibrated by, and another example, eccentric mass shaker. So okay, so we'll draw the figure. Without the figure we'll not be able to understand. So first we have to draw the figure. So there is a beam, yes, there is a beam like this, and this beam is vibrated by a eccentric mass shaker, like this. So and a given beam was vibrated by eccentric mass shaker of 5.44 kg. So this mass is 5.44 kg and the resonance was at 435 Hz. Then what happens? An additional mass was placed on this. And the new resonant frequency was at 398 Hz. Find the natural frequency of the beam without the shaker, that is due to its own mass alone. That means if you remove this whole thing, then what is the natural frequency of the beam? So you know first that while you have placed the shaker alone, so this is the natural frequency. So 1 by omega square, is 1 by omega beam square plus A11 M1. This is 1 by omega beam means, so in Dunkerley's method always remember the masses are to be placed one by one. So when you are using this, that means you have taken the mass of the beam alone, but you have not taken the mass of the shaker. And while you are doing this, you are not taking the mass of the beam, you are only taking the mass of the shaker. Only you are taking the stiffness of the beam. Here also you are taking the same stiffness of the beam. Here you are taking of the mass of the beam and not of the shaker. Here you are taking the mass of the shaker and not of the beam. So you are using this formula A11 M1, but you do not know the value of A11. They have not given you the value of A11. So what you do? But they have given you one additional data, so that when you put an extra mass of 4.52 kg, the additional mass is 4.52 kg of 4.52 kg. Then you put an additional mass of 4.52 kg, then you get this. So this is 1 by omega beam square plus this. So now this is the mass. Now you have got two equations and you have two unknowns, omega beam and A11. So you eliminate and you get the value of omega beam. So this is what you want. How much? And another interesting example is there. This is another interesting example. So a weight of 445 Newton. If you put a weight of 445 Newton at the wingtip of a fighter plane, that produces a corresponding deflection of this. If the fundamental bending frequency of the same wing is 10.38 Hz, approximate the new bending frequency when a 145 kg fuel tank is attached to the wingtip. Now when they give this, that this much of weight here gives the deflection of this, that means they are actually giving you the flexibility of this point. So the flexibility of this point is this. Okay, now they are telling you that if the fundamental bending frequency of the wing is, that means without the fuel tank, without the mass of the fuel tank, just due to the mass of the wing itself and the stiffness of the wing, this is the frequency, bending frequency. And now when the tank is attached to the wingtip, what would be the new bending frequency? That means, so this is the formula you have to use, 1 by wing square plus A11 M1. That means here you have to neglect the mass of the wing itself, but you have to take the mass of the fuel tank. So the actual the approximation for the first natural frequency is omega. So 1 by omega square is 1 by omega wing square plus A11 M1. That means here you are not putting the mass of the fuel tank, and that is given. What is the frequency? 10.38 Hz. And here you are not considering the mass of the wing, but the mass of the fuel tank. And if you sum them to these two terms up, then what you are getting is the natural frequency both with the mass of the wing and the fuel tank. So this is Dunkerley's method. So let us stop here.